Hello, my name is Trevor Canham, and I'm here for the 45th International Conference on Acoustics, Speech, and Signal Processing to present a paper titled Color Stabilization for Multi-Camera Light Field Imaging, which was written by Olivier Vu-Thanh, myself, Javier Vazquez-Corral, Raquel Rodríguez, and Marcelo Bertalmío. So I'd like to just start by giving an introduction to light field imaging. So the industry most of the problems that we work on in our lab comes from is that of cinema production. So as of right now, live action cinema is currently very heavily reliant on computer graphics material. So with that said, movie productions have to put a lot of effort into homogenizing these live action and computer graphics assets so that they look natural together. So light field technology is something that's very interesting to us as it sort of bridges the gap between virtual and live action material, and I'll explain how it does this. So light field images provide more in-depth information about scene light by capturing not only spatial information of the scene, but also directional information at each pixel. So this is accomplished by capturing the scene at a number of different angles, and then by taking the disparity between these images, we can learn something about the angle of light coming to each pixel. So this information can be used for a number of reconstructions and effects, including post-capture refocus, viewpoint change, 3D reconstruction, change of focal length, and super resolution. And these are all things that were previously only able to be accomplished with computer graphics material, and light field basically offers the opportunity for it to also be done with live action material. I'd like to show an example here, which was a piece that was produced by our project partners in the European Research Council Horizon 2020 project called SAUCE. So a multi-camera rig which was built by our partners at Saarland University was used to capture this material, and the post-production tools and processes were developed by our partners at Film Academy and the Vazquez lab at Trinity College Dublin. So these post-processing techniques are among the many open problems which need to be solved in order to make use of light field assets in actual production scenarios. One of these post-processing techniques, which is the topic of this paper, is the homogenization of color rendering between different capture elements. So in every possible light field capture architecture, there exists the possibility for color shifts to occur between views. So in order to properly execute these post-processing steps, and to get high quality light field images which don't have color rendering errors, these color shifts between views need to be corrected for. Generally speaking, the goal of color stabilization is to match between two images of the same scene which differ in terms of color rendering for some reason. These color differences generally occur because the images were captured with different camera models or were captured by the same model with variations in calibration or camera operation. In order to solve this problem, it really helps to consider how cameras render scene colors in order to summarize mathematically how they might differ from one another. The camera processing pipeline can be summarized in the following way. First, the sensor is stimulated by scene light to produce a raw RGB triplet, red, green, and blue triplet. Then, a 3x3 linear color transformation, which we call A here, and a nonlinear transform gamma are applied. These transforms can sum up any color rendering process which can happen in camera, but they also serve the purpose of transforming the raw values into a standardized color encoding space which can be understood by tools down the pipeline. Aside from some expectations which we'll talk about in a bit, this means that color rendering differences between two cameras can be for the most part summarized by a 3x3 linear and a nonlinear transform pair. Our method takes inspiration from this pipeline and the work of Hacohen and company, who introduced the primary step of locating pixel correspondences between images. So in summary, our method works by finding a set of scene correspondences between the test and reference images, the test being the image that you want to match to the reference, and then searches for the ideal nonlinear components, gamma 1 and gamma 2, required to cancel out the nonlinear encoding transformation applied by the camera, and then the ideal 3x3 linear color transformation H to bring the error between the pixel correspondences as close to zero as possible. We show here an example of a practical production scenario where our color stabilization might be helpful. Shortly after the man passes the camera, there's a change in the camera's exposure. So we use our color stabilization to minimize the jump, which the viewer can see here, to make it less distracting.
Other color stabilization methods use more complicated global color mapping techniques like optimal transport or Gaussian mixture models. However, we single out the work of Matisiak, who has proposed the only other light field adaptation of a color stabilization method to the best of our knowledge. This work offers a complete post-processing pipeline for planoptic light field images, one step of which is color stabilization. They estimate pixel correspondences using coarse-defined patch matching, followed by using the color transfer algorithm of Myrid-Grogan, which is based on a Gaussian mixture models approach.
So far, our method has only been used to match between a single test and reference pair, generally two images of the same scene from different cameras and different angles. In the light field case, things are a little different because now we have many test images that need to be matched to a single reference. So this is the primary focus of our method adaptation. The amount of pixel correspondences that we have between the test and reference image varies quite a bit depending on the position of the reference and the position of the test image. So if we have test images that are at the boundaries of the multi-view array, or at opposite boundaries of the multi-view array, their amount of correspondences might be significantly less than two views which are directly next to each other. So the first logical decision we can make is to choose a view in the center of the array as the reference, which can help us limit error in the method as it would result in the smallest sum difference from all of the other views. When large angular disparities exist from opposite corners of the multi-view array, we propose the use of a spreading method, like we show in the graphic here, where the first views to be matched are the ones immediately adjacent to the reference view, and then the views immediately adjacent to those views are matched, and we continue out to the boundaries of the array. We of course run the risk here of propagating error, but it in some situations may not be as bad as the error that we would get from the reduction in correspondences as we move towards the borders of the multi-view array. Another update that we made in this version, which is not expressly related to light fields, is the improvement of our method for dealing with scene elements that are too close to gamut and dynamic range boundaries. So earlier I stated that the camera pipeline assumptions that we make they don't hold in every single situation, and this is one of those situations. So the example I show here has, you can see that there's a color cast in the whole image, and then the white cloth around the bottom is overexposed, so it looks completely white. So if we applied a correction to correct the color balance in this image, it would now correct the balance of the white sheet away from white, which is not something that we want. So we add a secondary function which brings the correction towards identity starting after a certain chroma threshold. And as the chroma gets higher and higher, the correction matrix, the 3x3 matrix, is moved towards identity. When the matrix is at identity, no correction would be made. Throughout the development of our light field adaptation, we used the SAUCE project dataset, of which we've shown examples from throughout the video. In this material, there were shifts in the calibration throughout the array, as you can see in the raw images here. Evaluation of how accurately these images are matched to each other is a challenge, as each image varies slightly in terms of its capture angle, meaning that their differences cannot be simply evaluated on a pixel-by-pixel basis. Our solution then was to extract the values from the color checker chart, which is a matte surface, so it shouldn't vary too much depending on capture angle. So by taking the average value of each patch in each view, we can compare that to the reference and take the delta E 2000 color difference error. We'll present these errors in terms of their average for the entire array and all patches, as well as the maximum values. And we'll compare them to the results from Matisiak and company. In addition to the delta E, we also take the standard deviation for each patch between views as a measurement of consistency throughout the array. We had the opportunity to increase the speed of our computations by feeding our method downscaled images. So we repeated these quality tests for the different scaling factors to analyze its effect on method performance.
For the case of this dataset, simply matching each view in the multi-view array directly to the center reference, the technique we denote as center in the table, actually outperforms the spreading technique in terms of delta E, but not in terms of standard deviation. This could be explained by the fact that most of the correspondences that were found by SIFT here related to content in the center of the images, which was shared by all of the views. So the error propagation from the spreading method outweighs whatever benefit we had from increasing the correspondences by using the technique. We can also see that for our method there isn't a consistent trend in degradation related to the scaling factor. We can see that the full-size scaling does outperform the rest, but in many cases the 20% downscaling outperforms the 60%. For the case of Matisiak, however, their method degrades severely with a reduction in scaling, although we should note that they did not suggest using this technique in their paper. Overall, you can see in the tables that our method results in a lower delta E matching error and standard deviation across the multi-view array than the results of Matisiak. Our method also outperforms theirs in terms of computation time, as on a 2.4 GHz Intel i5 CPU with 16 GB of RAM, our method takes about 5 minutes to compute, whereas theirs takes on the order of hours.
Based on these results, we show that our method is a promising option for homogenizing color in light field post-processing. To its benefit, it requires no extra calibration steps during the capture process, and its transformation can be computed for the first frame of a light field video clip to be applied as a 3D lookup table to the remainder of the frames in the clip. Moving forward, we are interested in testing the method with a wider variety of test content, including different scene content, wide color gamut material, high dynamic range material, etc. Thank you very much for listening, and I hope you have a pleasant day.